Hello, and welcome back to Blockchain Fundamentals. In today's lecture, we're going to discuss how a transaction is propagated around the Bitcoin network, how when you make a transaction that we let other Bitcoin nodes know that you've made that transaction, and how these Bitcoin nodes can connect, disconnect, and otherwise interact with the network itself. In addition, we'll talk about some of the ways that the Bitcoin network has improved in the past and some of the limitations that we know will be facing Bitcoin in the future. So first off, when you create a new Bitcoin node, how are you supposed to know where the rest of the network is? How do you connect to the other nodes? So this is a well-known problem of trying to bootstrap something in an entirely decentralized manner. So there is a little bit of centralization involved in this. So when you first download the Bitcoin software, if you look at the code, you'll see a few different what they call seeds built in to the code. These seeds are simply locations of other nodes that have promised that they will be up online as much as possible. However, again, these are all in the code, and since Bitcoin is open source, you could theoretically modify them. So when you first try to connect to the Bitcoin network, your local Bitcoin node is going to look at these seeds, select one or more of them, and then ask it to send it some IPs of other Bitcoin nodes that are currently running. So if you look at the slide, you can see exactly where this code is located that has these seeds listed in it. So if you would like to check those out, please feel free. These seeds are pseudo-randomly selected. So you'll pick different nodes to connect to each time that you try to do so. The topology of the Bitcoin network is dynamic and random. It's always changing as Bitcoin nodes attached to the network go offline, come back online, or have other sort of problems like network connectivity issues. But the topology is always changing. So that little network diagram that I have on the top of the screen there is actually something that will change from continuously. But you'll find a few different nodes to connect to. So after this, you are now one of those nodes in the Bitcoin network. Now we need to discuss the gossip protocol. So the gossip protocol is relatively simple. It's basically just talking to your friends, talking to nodes that you're connected to about valid transactions that you know. So in this diagram, the node on the far left has made a transaction, and it now wants to propagate that transaction to other nodes. So eventually, all of the nodes on the Bitcoin network should know about this transaction. Note that at this point, we haven't put anything into blocks. So miners are going to package up these transactions and put them into blocks, but right now they're just living in what we call the mempool or transaction pool. So I broadcast a transaction onto the Bitcoin network to all of my peers. So those are the four gold-colored nodes in the diagram. Each of those nodes is going to check to see if that transaction is valid. If it is valid, it's going to pass it on to its peers. Besides you, of course, since you're the one who sent it to it. If it's invalid, then it'll just drop it. So what do we mean by a valid transaction? Well, first, we ask, is the transaction valid within the current blockchain? That is, if we take the script signature and the script public key, does it return true? Was this a valid transaction according to the rules of the current chain? Have the transactions that have been used for this not already been redeemed? That is, are they unspent? Have you not seen this transaction before? If you've seen the transaction before, then you'll just ignore it. And finally, is the script whitelisted? So while in theory, any Bitcoin script can actually be used for a Bitcoin transaction, in practice, nodes often will only allow a subset of these scripts to be considered valid transactions and passed on. So here we have a few examples. And when I pass this on, or a node, the second node sends on this transaction. So I was the orange node that originally sent it to the 4 gold nodes. That red node, this red and gold node, has 4 peers. Me, it's not going to send this transaction back to me. The other gold node that it points to, you can see that was also a peer of mine, and so it's going to ignore that hash. However, the 2 red nodes both see a new valid transaction they hadn't seen before. So they're going to add it to their own transaction pool and then pass it on to any of their peers, aside, of course, from the peer that's just sent it to them, the red and gold node. So it turns out this very simple protocol will actually eventually propagate to the entire Bitcoin network. So transaction propagation, though, is a relatively slow process. Something that you see again and again when talking about blockchain and decentralized systems in general is that decentralization and efficiency are often conflicting goals. Having a single centralized server is often much more efficient, at least in the short run. However, there are, of course, other problems that come with centralization, as we've discussed before. Block propagation has actually gotten much faster with recent optimizations and a lot of focus on this. And so most transactions will get to every or the majority of nodes, the vast majority of nodes in the Bitcoin network within a few seconds, as long as you have a good internet connection. Interestingly, the size of the Bitcoin network in terms of full nodes has been relatively stable over the last few years. So the number of nodes that need to be propagated to, it's actually relatively small. So we'll talk about, however, some of these other kinds of nodes that do exist, since not every node connecting to the Bitcoin network is a full node. So storing all of these blocks, right, the blockchain, as well as the temporary transactions that haven't yet been put into a block, the transaction pool, takes up a not insignificant amount of space. So as of this morning, when I checked, the current size of the Bitcoin blockchain was about 262 gigabytes. And this is monotonically increasing. What we mean by this is every block that gets added to this, it's never going to take away any of the previous blocks. We're always just going to increase in size. The size of the Bitcoin transaction pool has been a little over 5 megabytes on average over the last week, with a max of 25 megabytes a few days ago. I've included some links on the slide if you would like to look more into depth about where these statistics come from, and also see what the Bitcoin network looks like when you're watching this video. So I already mentioned that there were different kinds of nodes. When I showed Bitcoin nodes that were accepting transactions and were propagating them on to others and perhaps eventually trying to create their own blocks if they were also mining nodes, these are full nodes or fully validating nodes. So these are nodes that connect to the Bitcoin network directly and act as a full peer. They are going to need to download and verify the entire blockchain to make sure that any transactions that they propagate are in fact valid. Just as a note, downloading and verifying the entire blockchain is a not insignificant process, and depending on the power of your hardware, will probably take well over a full day or 24 hours to do. So these Bitcoin nodes are going to verify and propagate and perhaps drop invalid transactions, broadcast transactions themselves. They'll also allow you to verify, you as the owner of the node, to verify the entire Bitcoin network. This is the way to verify your Bitcoin transactions in the most secure way possible, running your own node. However, running your own node is a difficult process. It requires having hardware probably that is dedicated to it, or at least that is online for long periods of time, if not as close to possible as always. as well as taking up some CPU power and quite a bit of bandwidth. Also, to start using one, you are going to have to first sync up with the Bitcoin network, which is going to take, as we mentioned, quite a while, probably at least a day or two. So there are also other kinds of nodes known as lightweight nodes, or SPV nodes for simple payment verification. These are not as secure as a fully validating node. So instead of checking all of the transactions and all of the blocks themselves, they only download the headers of blocks, the metadata for the block, and checks that the blocks and hashes are valid, but not every single transaction. So this means that they're only ever going to validate transactions that affect them. They're not going to check the entire network for every single transaction. The majority of nodes on the Bitcoin network are, in fact, SPV nodes, since they are so much easier to run. So if you use a Bitcoin wallet yourself, chances are it's either an SPV node, or in the case of exchanges, that it's calling directly into the exchange and they're operating a node for you. So if SPV nodes don't provide as much security as running a full node in terms of being able to verify every single transaction, why would you ever run one? Well, first off are the rather significant savings in terms of storage and CPU usage. So we're talking orders of magnitude less CPU usage and storage compared to a fully validating node. You also don't have that very long lag time when you first start up a node that you get with a fully validating node. And when I speak of lag time, I of course mean on the order of perhaps days. So this is how Bitcoin operates now. But things change, right? We have determined a lot of different things about how the Bitcoin network should work and what the code should be like since Satoshi Nakamoto first released it in 2009. You have the ability to change Bitcoin yourself by filing a BIP, or a Bitcoin Improvement Proposal. I have a list of some famous BIPs, or rather useful BIPs, but if you would like look at the full list, I've included a link on this slide. So one of the more useful BIPs is BIP 11. Which added multi-sig support, that is multiple signatures, which we can use for escrow, which we'll talk about in a slide or two. BIP 13 added the P2SH, or pay to script hash, ability to Bitcoin. And BIP 141 added SegWit, or segregated witness, which does a few things, but perhaps most importantly, allows second-tier scaling to take place and increases the amount of transactions that can be held in a block. We'll talk more about SegWit later on in these lectures. So BIP 11. This is a little bit of a tangent, but I think is useful for understanding some of the usefulness of Bitcoin and blockchain as programmable money. So let's say that Alice would like to buy something from Bob, who is, of course, as the slide notices, a legitimate businessman. So Alice is going to send some Bitcoin to Bob, and Bob will send goods and services in return. And remember that Bitcoin transactions, once they are completed and on the blockchain and have a few blocks on top of them, are as close as one can possibly get to immutable. They're never going to be changed. So if Alice sends her Bitcoin to Bob, but Bob does not provide the services or send the goods that he said that he was going to, well, what can Alice do? Alice can't talk to the CEO of Bitcoin and say that the transaction should be reversed. So this brought about escrow transactions. So escrow transactions, we have seen escrow happen in real life in lots of different cases, where you give a security deposit to a bank when you're renting an apartment, for instance. And the bank will store that, and if both you and the owner of the apartment at the end of your lease decide that everything is okay, the bank never really has to get involved aside from just storing that money. However, if there is some sort of argument where you say that the landlord never fixed your sink and so you don't owe them as much money, or the landlord says that you had a party and destroyed their walls or something, well, then the bank can act as the arbiter on whether or not the renter should be able to get back their money. That money was kept in escrow. So we actually can do that in a decentralized way. So in this instance, we've added Judy, who's a third-party arbiter. And instead of creating a single transaction here, we're actually going to pay to a script hash. So in order for this particular script, in order for it to be, the money to be sent from Alice to Bob, needs to be signed by 2 of the 3 members of this triumvirate, if you will. So assuming that everything goes well, Alice buys something from Bob, Bob gives Alice the goods or services that she has requested, then both of them can sign off on the transaction, and Judy doesn't even have to get involved. However, if there is a disagreement, Judy now has a way to either sign off the transaction, in which case the Bitcoin will go to Bob, or not sign off on it, in which case the Bitcoin transaction never goes through, and so Bob never gets his Bitcoin. Obviously, you are now putting some faith in Judy, and it might be something that you'd want to verify that Judy is not acting in cahoots with Bob or with Alice behind the scenes, but it does provide a way for people to transact a little bit less trustlessly with others while still maintaining pseudonymity. We also see changes in the network in terms of forks. So a fork there are 2 kinds of forks. So first off, a hard fork. And this is where new features get added to the blockchain that were previously considered invalid. So previous versions of the software won't accept new blocks, but the past is shared between the 2 blockchains. So this can lead to chain splits. So for instance, with Bitcoin Gold, when this forked off from the original Bitcoin, everybody who had, say, 1 Bitcoin also had 1 Bitcoin Gold, because up until the point of the fork, they shared history. However, going forward with Bitcoin Gold, in order to get more, you used a different hashing algorithm that was supposedly ASIC resistant in order to produce blocks on the Bitcoin Gold network, while the Bitcoin network continued to operate using the SHA-256 hash that it still uses to this day. Hard forks do not necessarily mean that you are going to create a new blockchain. So for instance, Ethereum and Monero hard fork often, upgrading their network in various ways. And if you would like to continue using those networks, you need to make sure that you upgrade your software as well. Soft forks operate in a different way. Rather than introducing new features that previous software would not recognize, instead, you are making the validation rules stricter. So you are reducing the amount of what will be accepted going forward. This means that previous versions of software are still going to accept blocks created by the stricter rules. However, these new blocks may not accept blocks produced by these older nodes. So there are benefits and drawbacks to using hard forks. We'll discuss a little bit later. We discuss more about altcoins and some of these forks that produce new coins in a few lectures. So how do people decide on whether or not a soft fork should occur or some other change should occur? Well, right now with Bitcoin, this happens off-chain. And there are different ways to signal whether or not that miners can signal whether or not they would like to continue with one direction or another, or that different nodes can say, again, sort of vote informally on which direction to go in. And if all the nodes accept the changes, that change goes forward. However, if nodes don't accept that, they don't update, they want to keep working on their own, they can follow this different fork and fork off from the main network. This is always an opportunity for nodes to continue using the old software and continue off on their own. It doesn't happen very often. It's not as though every upgrade, there are some people that decide not to upgrade for ideological or other reasons, but it does happen, and there have been a few very famous instances of it, which again, we'll discuss more when we talk about altcoins. So that being said, now that we've discussed hard forks and soft forks and how the Bitcoin network operates, are there any known limitations or issues with Bitcoin and the Bitcoin network? And the answer is, of course. There is no perfect software out there. The only perfect software is software that doesn't exist. Right? So there are some known implementation bugs. So for instance, a multisig instruction is always going to pop off multiple values off the stack when it really should just pop off one. And so people have just learned to live with it in their multisig scripts. We know that the number of transactions on Bitcoin is relatively limited because we have 10-minute blocks and we can only store so many transactions per block. It turns out we have a theoretical maximum of about 7 transactions per second in Bitcoin. We have fixed cryptographic hashing algorithms. So if we determine that there are other hashing algorithms that might be better used, there's really no way to upgrade that absence of a hard fork. We also know that there are a few other minor issues. So for instance, 1 Bitcoin can be divided by 100 million. It's the equivalent of cents in Bitcoin, except instead of dividing by 100, you divide by 100 million. The smallest unit of Bitcoin is called the Satoshi. As of right now, there's no way to, on the main Bitcoin network, to have a lower divisibility or smaller units than Satoshis. If we imagine that Bitcoin goes up to, say, $100 million per Bitcoin, that also would mean that the smallest unit of division, a Satoshi, would be worth $1, which, as you can imagine, is suboptimal. There are only so many operations that can occur per block. We can only have so many transactions per block. There's the year 2106 problem. So at the year 2106, which is coming up, it's only 80 years away or so, we are going to have some issue with the timestamp since we use an unsigned integer to store it, and we store the number of seconds since the epoch. What you'll see is that in other similar systems, they hit this problem in the year 2038. We're going to hit that problem in the year 2106. Now, some of these may be modified, especially if we're using Bitcoin in year 2106. We're definitely going to want to do something to fix that. However, there are a variety of factors that are not likely to be modified because they're so ingrained into the Bitcoin network. So for example, the number of Bitcoin produced. The maximum number will probably will always be 21 million. The mean time between blocks. The block rewards given, the halvenings that occur. These are very unlikely to be modified. And for any of these limitations, they're probably difficult or impossible to fix without a hard fork. The Bitcoin ecosystem as a whole is not a big fan of hard forks, and so we don't see these issues being modified anytime soon. In the next lecture, we'll discuss more about the Bitcoin network and some of the mechanics of Bitcoin.